This is room 1. Let me see if
some of the questions. Great.
Host. Professor Koseglu will be the chairman. And
yes, I'm here.
Speakers.
I would like to thank the organizing committee who gave me the opportunity to chair this session. And as I can see, we have to move forward to the next talk, which will be given by Miss Immaculada Leyva.
Yes, here I am.
Okay.
Let me make you. There you are. Yeah. So you are being made also a co-host, Ms. Leyva, in order to be able to operate. Yeah.
Okay. Perfect.
Okay, and she will present how easy is it to be a hub and what the dynamical complexity can reveal about the network structure. Give me some minutes in order to. Okay, so you're ready. You may proceed.
Okay, are you seeing the slide?
Yes, we can see it.
Yes, very good.
You have 27 minutes in order to present your presentation.
Okay. Okay, thank you very much. Thank you to the organizer for inviting me to give this talk. I'm going to tell you about this work that we made in collaboration with our friends in Mexico and my group in Madrid. Okay, the idea is the following. As you probably know, for a long time, when we have a network, a dynamic network with dynamic in the nodes, we essentially in our community are been doing two kind of things. Okay, one of them is looking for the collective dynamic. We look to the relationship between the structure and the dynamics, and then we try to see how these two things relate in a collective dynamic, essentially synchronization. More or less, we have made a lot of works about this. We know we have a huge corp of works about this kind of thing. Okay, this is one of the kinds of things we used to do in this kind of network. The other thing can be, in a nutshell, be called the pairwise correlation. Okay, we see we take the nodes 2 by 2 and see their dynamics, how they correlate. And from this, we can do several things. For example, try to deduce how they are connected. We try to infer the network itself, all the links. We can use it in application. Like, for example, I'm giving you the example of functional bring network, etc. That kind of thing. And now, as you probably know, we are introduced ourselves in not so pairwise correlation. We are doing non-didact correlation, high order correlation, as you want to know. Okay, this is essentially what we are doing in this in network for a long time. But I would like to think to try to do your thing in another kind of way to see the thing, because whenever a node with a dynamic is inside the network, this dynamic is being modified by the same fact that this node is inside a network. Okay, the node is not behave in the same way that it will be in isolated state. Then try to think then not what are you doing for the network, but what are the network doing for you, for saying in this way. So the idea is, from this modification, can we say anything about the network just from the dynamic of a single element, not by pairs, not by collective, no, just looking at one of them, see if with this single dynamic we can say anything at all. Okay, that's the idea. Then For this kind of work, we need a tool, whatever tool for analyzing the dynamics. And in our case, this tool is going to be the statistical complexity. Okay, I can imagine that more of you know about this measure that I'm going to explain very briefly what that means. The statistical complexity was proposed in 2004 and it's a product of the two different measures. One of them is the normalized Shannon permutation entropy, and the other one is the permutation disequilibrium. As you see, both of them are relating to a kind of measure, which is the permutation ordinal pattern. Then I'm trying to explain also very briefly what that means. This kind of way of analyzing a time series, it was proposed some time ago in 2002, and the meaning is more or less the following. You have the dynamics that I have represented here, and you have to sample these dynamics in a way that can be very varied. You can use a periodical sampling, you can use a map, you can use, it can be very various, okay? In this example, I'm going to use just the maximum, okay? I'm going to forget all the rest of the series. I'm taking just the maximum, okay? And then when I have done that, then I have to choose a number for dividing my series in smaller groups that are going to be my pattern size. Okay, in this example, I'm going to use 3. Usually it's larger because 3 in fact is very small, but it's just for the example. Okay, then divide this series, the maximum series, in parts of 3. Okay, and then you have to here I have represented it by colors, and I have all the maximum values divided in groups of 3. Then in each of these groups, you have to look for the order in which these values appears. For example, see the blue group, the first one, and see that the maximum of the 3 values appears in the first place, which is the 13.1 in this case. The second value appear in the second place, and so on, okay? But for example, in the second group, the red one, the maximum of them appears in third place, okay? That's the idea. And then you have to substitute your series for the order in which each of the value appears in the smaller group. Then you can forget the series, the original series, and then you have the ordinal series. See that this is now independent of the original model, okay? Just you have the order inside the groups, okay? This usually has to be a very long series from which you can obtain the pattern probability distribution, meaning that you see how often appears any of these orders of this pattern inside the series. For example, in this example in which the order is 3, you can have factorial of 3. This is 6 different possibilities, and then you see how often appears the 1, 2, 3 possibility, how often appears the 1, 3, 2, etc. Then you obtain a distribution of this pattern, and this is going to be the final analysis for your series. Once you have the probabilities, you can go to the values I have showed you before and calculate the normalized Shannon perturbation entropy of these probabilities. Here are the pi sub I, and you can also calculate the disequilibriums. The disequilibrium is slightly more complicated calculation, but essentially measure how far is the distribution from equipartition. If the series is periodic and then the pattern is always the same, then the disequilibrium is very high. If it's completely random and then all the patterns appear with the same probability, and then the disequilibrium is 0. Okay, that's the idea. And finally, you calculate the complexity. The complexity, which is a product of these two things, is related on how predictable is the series and how much information contains. See that, for example, if the series is periodic, then the complexity is going to be 0. But if the original series is completely random, then the complexity is again 0. And the interesting kind of series is in between all these kind of things. Okay, this is going to be my main value for a temporal series. Then, as I'm going to calculate this value for each of the nodes of my network, then I can try to reduce all this information, having the guess that all the nodes that have the same degree are going to behave at the same way inside the network. That's the idea. And then I can calculate the complexity, the average complexity of the node. This is going to be C sub k. This is the degree complexity, okay, for my series, just to have a reduction of my temporals of my series. Okay. Then, of course, in my network, I'm going to, I also want to know how synchronized is my network. Then I'm going to calculate also the synchronization error, of course, and the phase synchronization parameter when it's appropriate. Then that's the idea. Then let's go to the calculation, beginning for the simple scale, the star network. In the first example, I'm going to take a network which has just 30 nodes. All of them are identical, are chaotic Roxler, and I'm going to do the calculation I have shown you before. And first, the synchronization. Of course, the system, as expected, first became phase synchronized, and if you increase the coupling, then it became completely synchronized. That is, of course, the expected behavior. But what's happened with the complexity of the nodes? What happened is the following. In this case, we have only two kind of nodes, the leaf and the hub, and then we are going to have only two values for the C sub k for the complexity by degree. Okay, and as you see, the path that the leaf and the hub record along the process, the path of synchronization is very different from the view of the complexity. While the leaf essentially maintains its value all along the process, the hub instead have a drop in the complexity immediately after of the coupling. Then this is a strong difference between them. But what is really happening? What is if we take a microscope and see the attractor of each node, what is really happening? Of course, at the beginning, both of them, if I project the attractor, both of them have the same attractor. That's obvious. But when I coupling a little bit, then they look completely different. While the leaf is more or less the same at the beginning as expected, the drop, the hub has become essentially a limit circle, a noisy one, but the attractor has completely changed the behavior. When the coupling is slightly higher and the two nodes are phase synchronized, they still are completely have completely different dynamics, and the hub is still much less complex than the hub. Slowly, the hub recover up to the final state, which is of course exactly the same at the beginning. Okay, but see that only with this measure you can tell apart which of them is the hub and which of them is the leaf without without making any pairwise correlation. Okay, this is just for having the idea, but we want to see this in largest network. But before, we run to the lab and try to see if this is really happening in the experiment. In our case, the experiment is an electronic Rossler-like oscillating circuit. In this case, we have just 8 of them. And what we see is essentially the same. Okay, then we have the tranquility that this is really happening, and then we are ready for going to largest network. Okay, this is the result for a slightly larger network. In this case, it's going to be 150 nodes. For having the most heterogeneity in the degree possible for this kind of network, the structure is obtained by the Barabasi-Albert algorithm. Okay, and the rest is the same. That's is Rossler, etc. Then this is the result. Here we have all the good curves together, but as you can see, the idea is the following. Before the system became phase synchronized, the complexity of the nodes that at the beginning was exactly the same, of course, split like a rainbow in groups divided by the degree, in such a way that those degree, the larger the degree, the smaller the complexity. Okay, all the values became again the same more or less when the system is phase synchronized. But for this weakly coupled regime, we can divide the nodes by its complexity. In fact, if you do the opposite plot and for a fixed coupling, in this case, this correspond to this value, this very, very small coupling, then you obtain that the complexity depends practically in a linear way with the degree. That means that you can use this calculation as a proxy for the degree distribution. See that we are not calculating the individual links. Okay, we are not able to infer the network. We are not able to give any details about the structure. But with this only measure, which is individual and notice is not pairwise, we are able to say which nodes are the most important. Okay, and often this is the only thing that you need. You are not going to need each link individually, but you only need to know what are the important hubs. In this case, the important hubs are those we have the smaller complexity. This is slightly counterintuitive, but this is the answer for the question in the first slide. How difficult is to be a hub, but not. Well, the answer is not very much. For weakly coupled networks, very far from synchronization, the hubs happens to be the less complex in this sense that we are telling here. Okay, that's the main result. Then we have done several robustness checks. For example, we have tried with a network with different average degree, and the results, once you normalize the degree, normalize the coupling, then the result is exactly the same. You can also try with not identical nodes, which is a very important fact, because if you in real application you are not going to have identical nodes, but still the result is the same. And if you change the dynamics completely, for example, here is a result for Lorentz nodes. Again, the result is the same. You have this split in the complexity of the former node. Then it's saying that is quite robust, and it can be tried in different data that maybe it's inspiring you for trying something similar in your data. Okay. Can we say something analytic about this, something that can give us an idea about what is really happening? Okay, this is, I'm going to try to give you the idea. It's not very rigorous, but probably it's quite intuitive. Okay, imagine this is your dynamical system for the network and the market. Look at that here. I'm supposing even that the nodes could be different. Okay, that's a quite general dynamical system that is in principle is a Laplacian one. Okay, that you have here the structure and this term that ensures that the system is a Laplacian one. Okay. Then from this system, you can calculate, for example, the local main field. Okay, you take a node and see what is the average value of the dynamics of its neighbor, for example. Okay, but you can also calculate the global main field, okay, the average of all the dynamics. If a node is a highly connected one, then these two things are more or less the same. Okay, then you can take the approximation that the hubs, the local main field is more or less the same that the global main field for the hubs. Okay, then for those nodes, you have then the approximation of this kind of calculation. Okay, this is the equation, the dynamical equation for the hubs. Then another simplification. In the weakly coupled regime, the global main field is very small or a constant value. Then we can reduce this term. We can take it off to see that the following: the remaining equation is just the isolated value, that is this function here, less this term. This term, as you can see, happens to be a negative self-feedback. Okay, it's just the same dynamics that is self-feedback in the node. Okay, as a negative self-feedback, just as you probably know, is a very old method for orbit stabilization. So it's not surprising, it's in fact a quite well-known fact that the hubs are losing the complexity and becoming, if the original was a chaotic dynamics, in the weakly coupled regime, the orbit stabilized, and if this was a chaotic, then becomes periodic or that kind of thing. Okay. If you prefer the linearization, you can linearize around the mean field. Then you are going to have this linear equation where J is the Jacobian of the dynamics. Okay, and from this you can calculate the Lyapunov maximum Lyapunov exponent, and you are going to obtain something like that, where this lambda sub 0 is the Lyapunov exponent when the node is isolated, and this modifying term, which is proportional to the coupling and to the node degree. So in fact, as you see, the Lyapunov exponent is going to be less than the original one, and then that is becoming also another clue of orbit stabilization. Okay, I think that I have been very fast. Okay, that's just the conclusion. I'm trying to make you see that this statistical complexity for the dynamic of the individual node can give you information about the topological role of the node. Okay, can you not give details about the structure, but it can give you information about how important is the node inside the network. Okay, this structural information can be obtained without computing pair-weight correlation that usually are very heavy computation. but this is fast, it is easy to calculate, and maybe can be useful if you don't have need of having a lot of details about the structure. Okay, and the result is that hubs tend to show less complexity than peripheral nodes. But this could be maybe unexpected. But for example, here I have an example in real data for functional brain networks that happen to obtain the result I have shown you here. Here in this case, in this real data, this is the strength of the node that has been calculated by another kind of means and happen to have an obvious correlation with the complexity. So it's seen that it can be found in real system. Okay, and I think that is going to be all. Here I show you some related publication. This is the main one, and a couple of other more that can be of interest for you. And that's all. Thank you very much.
Thank you very much.
Very
thank you very much for being on time, Ms. Leyva. So the session is open for questions. Are there any questions for the interesting presentation of Ms. Leyva?
Yeah, so if I can
yes,
ask.
please.
So thanks a lot for the nice talk. I was wondering, so the way you showed it right now seemed to be for undirected or bidirected networks. If we look at directed networks, would this only rely on the in degree, or would there be additional complexity?
I have not done, but my intuition is going to be to give you an idea of the in degree. Okay, that is the reason is. Let me show again. No, this is not here. Okay, probably this equation will be the same, but with this part will be the in degree of the node. Okay, which is the part that is going to modify the dynamics of the node, the node you are studying. So probably the result is going to be the same, but gives you information about the in degree. But I have not done myself, just my intuition.
Good, thank you.
I don't know.
Thank you. Are there any other questions?
Yes, I have questions. You showed this nice thing for this oscillators, Roslo oscillators. Will it also work for different oscillators?
Mm-hmm. I have shown you also this one, which is with Lorentz nodes. See here? I don't know if you're seeing the...
Yeah, I've seen.
Okay, this is for Lorentz nodes, but I have done it also for, let me show you another thing that I have not time. This one is for Morris-Lecarne error, which is not, I don't know if you know this kind of...
Yes, I know.
error.
Yeah.
Okay, that's in this case, the coupling is a time pulse coupling, and therefore it's not a Laplacian one. But still, then here happened that it's still working, but as is this in this case, the network is the node is a stochastic one, so it has noise inside. Mm-hmm. Then it has two regimes. A first one, which is noise driven, in which the complexity of the hubs is higher than the other part, than the other nodes. And then once the system overcomes the noise-induced dynamics, then again we have the same result. The hub is less complex than the other. Then if the system is more complicated, in particular, if it has noise inside, then the result can be a little bit more complicated due to this noise-induced dynamic in the very weakly coupled part. But once this is overcome, the result is still the same. So as far as I have seen in all the system I have tried, the result is more or less the same, qualitatively the same, with different peculiarities, but it's the same.
Thank you. Very interesting. Yeah.
Thank you.
And thank you very much. I suppose there are no other questions. Okay, Ms. Leyva, really thank you very much for a very interesting presentation. And we should, thank you. We should continue with the presentation of Mr. Oriol Artime. Am I right?
Yes, I'm here.
Okay.
Can you hear me?
Yes, we can clearly hear you.
Perfect. So I'm going to share my screen because it's recorded.
Yes, please. You are co-host.
Okay.
So Oriol Artime will present percolation on feature-enriched interconnected systems.
Okay.
And you have 12 minutes in order to present your presentation, and after that to discuss about your talk.
Okay,
please proceed.
I'm clicking play. If there is something wrong, just tell me, okay?
Okay, okay.
So good afternoon, everybody. I'm Oriol Artime. I'm a postdoc working in Fondazione Bruno Kessler in Trento, Italy. And today I'm going to talk about percolation, in particular on how to account for non-topological information when attacking or dismantling a network. So first thing first, what is percolation? Well, it can be seen as a process in which we have an interconnected system and we remove a given fraction of nodes in order to study the properties of the remaining network. And why this phenomenon is important, on the one hand, from a theoretical point of view, it represents the simplest model of a phase transition. But on the other hand, percolation is really a flexible model that can be mapped to very, very diverse phenomena. Therefore, a solid knowledge about percolation helps opening the doors to tackle interdisciplinary problems. One of these problems precisely is the one of network robustness, which is the motivation of our work. I said that to study percolation, we need to remove a fraction of nodes. So we need to devise removing protocol. The classical protocol is to select nodes uniformly at random and remove them. But when we have complex networks, there are a bunch of topological descriptors that are heterogeneously distributed, which allows us to sort nodes by their value and removing them following that order. And these two protocols have been largely studied and are very well known in the literature. However, nodes in a real network, in a real system, might be characterized also by a non-topological descriptor that can be heterogeneously distributed as well, and accordingly, we could remove them, or could remove the nodes following that order. And we call these node metadata. We call them the node feature. That's why we called our framework feature-based percolation. So you might ask, what is a feature? So here I'm giving two different examples, two non-trivial examples between two non-trivial patterns between degree and feature. So the first one is related to Wikipedia, from which we built a network with the nodes being articles and edges are hyperlinks between articles. And the feature here is the number of single editors per article. And we found that there is a positive correlation between that feature and the topological structure of the network. Another example, this time negatively correlated, is related to Twitter, where we found that the number of shared fake news decreases with the visibility of the users. So the research question that we want to address in this work is the following. Can we develop a theory of percolation that takes into account both topological information and node features? The idea is to conceptualize the possibility of attacking a network with these new feature-based protocols, and in order to provide a mathematical framework that can help unravel unexpected responses and hidden fragilities. So in this slide, there are the mathematical ingredients of our framework. I'm going to be brief here. We have to have a vector of feature for each node, where features can be discrete of continuous. We have also the typical degree distribution per node, and we have a new feature distribution per node. And these two distributions can be both obtained from a joint degree feature distribution. Finally, we have the occupation probability phi that gives the probability that a node with degree k and feature value f is present in the network. So I don't want to lose a lot of time in here in the mathematical details. The important information is that the size of the giant component depends on the joint PDF. So we need this quantity in order to compute the size of the giant connected component and other percolation quantities. And I'm going to present for the rest of the talk 3 examples where we compute this size of the giant component. And the first example is an ad hoc joint degree feature distribution, for which we can control the correlation strength via tuning some parameters. Also, I'm going to present an example where the features are related to the network construction. And finally, I'm going to close by showing an example where the feature is related to a dynamical process running on top of the network. So the first example, and it's also the easiest one because we have we already have the ad hoc distribution. We are going to, I'm presenting here the example for a distribution that has a positive correlation between degree and feature, and one that has negative correlation. And what I'm showing here is simply that the match between theory and simulations is very good. So we can't account for these feature-based attacks. And for each type of correlation, I'm also showing the curve for the networks with the feature values reshuffled or randomized. And we observe that not taking into account the correlations might produce important deviations, and positive correlations behave quite differently than negative correlations. The second example is the one of feature related to the network construction. For this, we built two-dimensional random geometric graphs. And for those of you that don't know what they are simply nodes embedded in a plane, and links are drawn between nodes that are separated by a distance smaller than a fixed value. This is called the radius of interaction. And we construct such a network, and we take as a feature the distance between the node and its closest neighbor. If the closest neighbor is at a distance smaller than a radius r0, then the central node is removed. Therefore, we end up with a network in which there are links connecting nodes at a distance between 2 radius. This scenario can be relevant, for instance, in spatial ecology, or where species compete for resources. And we apply this removal protocol to random geometric graphs, and we see that the match is still very good. As a final example, we identify the feature with a dynamical process running on top of the network. Let's consider xi is a quantity defined in a node I, whose time evolution is given by this dynamical system. And well, this dynamical equation have a steady state, and we identify the feature of each node with the value of each. We identify the node. We identify the feature of the node with its value in the steady state. Okay. In few cases, we will be able to compute the joint PDF, but in general, this information is not accessible easily. However, we can make some assumptions to get an approximate PDF and apply our framework in this type of problems. And here there is an example. We simulate down here an SIS model and look at the steady state as a function of the degree. And we see that for each degree, the distribution looks like a Gaussian, or it looks like can be well approximated by a Gaussian distribution with a variable mean, a variable width, and a variable height. So the challenge then is to compute the mean, the width, and the height. To do so, we employ the Bayesian machine scientist, which is a recently introduced algorithm based on Bayesian probability and Monte Carlo Markov chains, but it is able to provide the most plausible closed form given the most plausible closed form, so a function that given a data set. To get the mean value on the width of the Gaussian, we project the data of the histogram and apply the algorithm to the data, which is able to provide an analytical expression in an unsupervised way. And we do the same for the height of the Gaussian. In this way, we have an approximate expression for the PDF, and we can plug this expression in the expression of the size of the giant component. So we use this approximate PDF, and we see still that the match is quite good, despite of the approximation and the assumptions employed here. So you can ask, well, what about other dynamical processes? Not this works only for the SIS or works for other dynamical processes? And what happens on real networks, on real topologies where you have correlations, for example? This also works. So here I'm to close the talk, I'm presenting two different examples of other dynamics in real networks. The first one is I'm using this population dynamics given by this expression. And in the real network where we run these dynamics is the network of competition and cooperation of pollinators in the US. And yeah, we can observe that the agreement within theory and simulations is still quite good. And the pipeline to obtain the size of the giant connected component has been the same. First, to simulate the dynamics, you compute the steady state. Then for each degree, you compute the distribution of features with the Bayesian machine scientists. And from there, you compute the mean, the width, and the maximum of the distribution. And from this distribution, we get the joint PDF, an approximate joint PDF. We do the same for a model of biochemistry, and we apply this model. We run this model in the network of the C. elegans interactome, and we see that our framework is still is capable of reproducing the results from the simulations, and the agreement is quite good. And with this, I want to conclude by giving some take-home messages. So here I have presented a framework to study percolation based on features. These features can be identified with node metadata of different nature. For example, metadata can be either an exogenous or endogenous property of the node, can be either a constant or a mutable nature, can be either numerical or non-numerical, etc. So it's really a flexible framework. The main quantity that allows us to compute the percolation properties is the joint PDF between the degree and the feature. And this is possible in certain cases, but not always. But we have found a way to overcome these limitations employing machine learning techniques. And finally, I want to stress the fact that here I have focused on node percolation, but this framework can be easily extended to study other settings such as bond percolation, percolation in multi-layer structures, in networks with clustering, etc. So with this, I want to conclude. Thank you for your attention. And this is currently a work that is under review, and we hope that in the following weeks or months, it will be published. So thank you for your attention, and goodbye.
Thank you very much for your interesting presentation. And the session is open for any question.
Oriol, can I ask you a question?
Sure.
Isn't it the basic thing that you're looking at, the point where the largest cluster crumbles, it disintegrates, and you call that the critical point? Is that correct?
Yes.
And the percolation transition probability is at the point where the largest cluster ceases to exist, yes?
Exactly. Yes.
Okay, good. So let me ask you something. It used to be a long time ago, maybe over 10 years ago, that some people had devised a formula which was dependent only on K. They called it factor kappa, a factor kappa, which was a function of K. That they said that when this value of kappa is over 2 or is under 2, then it goes through a critical point. Can you compare, or is there any comparison at all with what you have done here?
Yeah, so that I think this factor kappa is just a ratio between the moments of the degree distribution, right? Or am I wrong?
This is what I remember. Yes.
Okay. So yeah. So this is so yeah. So what we have done here, it's just, you can see it as a generalization of percolation, where we combine topological information via the degree distribution, and we also can apply some, let's say, attacks to the network via the feature distribution, which is a quantity defined in the nodes. So I think that this factor kappa that you are mentioning, it just, if I remember well, it was for percolation, random percolation, right? So nodes chosen at random, and yeah, the critical point was related to the degree distribution.
Okay, thanks.
Yeah, okay.
Thank you. Are there any other questions?
Yeah, I see here in the chat, right?
Are there any?
Yeah, can we predict the critical
There's some in the chat, yes.
Yes.
So yeah, the question is, can we predict the critical exponents from the phase transitions observed? And the answer is yes. So you can, since you have an analytical expression for the size of the giant connected component, if it's simple enough, you can do some expansions and get the critical exponents and the critical exponents and the universality class. We have done this for the uncorrelated case, and we obtain the same universality class than the classical percolation, and we expect to do so for the correlated case between degree and feature. We don't know yet in the correlated case what's the universality class.
Okay, great. Are there any other questions? Okay, we're still on time. So thank you very much, Oriol.
Thank you. Bye-bye.
Let's go to the third last oral presentation for this session, which will be given by Yanchen Liu.
Hi, I have a recorded presentation. Let me share my screen.
Yes, for sure. You have 12 minutes for your presentation in order to have 3 more minutes to discuss. So whenever you are ready.
Hello, everyone. I am Yanchen Liu, a PhD student at Northeastern University. Today, I'm going to talk about network symmetry. So first of all, what is network symmetry? Here I'm showing 3 examples of networks that are intuitively symmetric to us. So the next question is, how do we formalize our intuition that they are symmetric?
Oh, sorry. I'm sorry about that.
Okay.
Hello, everyone. I am Yanchen Liu, a PhD student at Northeastern University. Today, I'm going to talk about network symmetry. So first of all, what is network symmetry? Here I'm showing 3 examples of networks that are intuitively symmetric to us. So the next question is, how do we formalize our intuition that they are symmetric? An important step in formalizing a network symmetry is that noticing that there's a common feature in these networks, which is that there exists sets of nodes in these networks that are equivalent to each other, which in other words means that they can be interchangeable to each other without changing the network structure. Formally speaking, if a network is perfectly symmetric, then there exists a node permutation P, which permutes node I to Pi that preserves the adjacency matrix of the network. Such node permutation P is called an automorphism of the network. For example, in this example network here, there exists such node permutation, which permutes node I to 2, permutes node 2 to I, 3 to 4, and 4 to 3. And after node permutation, the network stays exactly the same. Specifically, preserving a adjacency matrix means that if there is an edge between node I and j before permutation, which means that aij is 1, then there is also an edge after node permutation between node pi and pj, which means api pj is 1. Similarly, if there is no edge between node I and j, then there is no edge after node permutation between node pi and pj. A node permutation P can be represented by a node permutation matrix P. So for example, in this node permutation that is represented on the left, it can be encoded in the matrix on the right. So in this matrix, there are 4 non-zero elements here, P12, P21, P34, P43, which represents permuting nodes between node 1 and 2 and 3 and 4. So now that we have a definition for perfect network symmetry, the next question is that enough? Here I'm showing 4 examples of networks. The first network is a 2D lattice network, which is perfectly symmetric. It has a perfect symmetry, so it will be classified as symmetric. The second network, however, is the first network with 1 missing edge. So if we only consider perfect symmetry, then this network will be classified as asymmetric. However, intuitively speaking, we still feel like there is a certain level of symmetry in this network, even though it doesn't have a perfect symmetry. In the third network, it has a perfect symmetry because it's a ring lattice. However, in the fourth network, it's the same network with 2 missing edges, which makes it asymmetric according to the definition of perfect network symmetry. So this prompts us to come up with definition for not just perfect network symmetry, but also approximate network symmetry. So why is that important? Why is approximate network symmetry important? It is because that, especially in the cases of real-world networks, perfect symmetry for especially a large set of nodes and edges imposes a very strict limitation that is hard to be met due to the stochasticity of networks, especially for real networks. So how do we measure approximate network symmetry? Here, for example, is a network that has a high level of approximate network symmetry, but no perfect symmetry. And this is its adjacency matrix. Now let's do a node permutation for this network, which permutes the upper half of the network to its lower half. And here is the network after node permutation. Notice that one edge in the original network in the circle there is not preserved after the node permutation in the circle in the permuted network because it doesn't exist anymore. And this permuted network has adjacency matrix PA/P transpose, where P is the node permutation matrix. And note that these 2 adjacency matrices have different non-zero elements, and the absolute difference between these 2 matrices is 4. So in this node permutation example, one edge is not preserved, and the absolute difference, which is the norm 1 difference between A and PA/P transpose, is 4. So this means that each unpreserved edge is represented by 4, a difference of 4 in the 2 adjacency matrices before and after node permutation. So this gives us a way to measure approximate network symmetry, which is defined as EA, which is minimizing over different possible node permutations that minimizes the difference between adjacency matrices before and after node permutation. So this EA effectively means the least number of edges that are not preserved in any possible node permutation. So if a network is perfectly symmetric, it has EA equals to 0 because we can always find a node permutation that preserves all edges in the network. And the more symmetric the network is, the lower its E is. Also, we can normalize E by 1/2 of n choose 2. The reason behind this is because after this normalization, SA is always less than 1. So after we have this, now that we have this definition of network symmetry, we applied it to 4 different network models as well as several real-world networks. First network model is ER network. So here we are measuring ER network samples from G and M ensembles with n equals to 100. So first of all, here we can see that when m is 0 or n choose 2, they always have s equals to 0, which means that for empty graphs or complete graphs, they always have perfect symmetry. And s reaches its highest when m is 1/2 of n choose 2. And also this curve is symmetric around the middle point, which suggests that ER networks from ensemble G and M and G and n choose 2 minus m have the same level of symmetry. This can be proven rigorously, but I'm not going to do that here. The second model that we looked at is the random geometric graph. Here we're showing s as a function of m as well as the connection radius r. And we also showed s for ER networks as a comparison. So we can see that our GGs with or without periodic boundary conditions are always more symmetric compared to ER graphs. Right here, showing examples of RGs without periodic boundary conditions at a lower and a higher connection radius. So one interesting thing is that at r equals to 0.3 in the node permutation matrix P on the right here, most of the non-zero elements are located around the diagonal of the matrix, which means that a node is very likely to be permuted to another location that is very close to its original location. This can also be observed by looking at the node colors in the permuted network. And you see that the node colors are not that different from the original node colors, which means that only local permutations are made. The third example is Wasserstragas networks. Here we measured s as a function of number of edges m as well as the rewiring probability p. And we can see that Wasserstragas networks are less or equally symmetric as ER networks. And as the rewiring probability increases, more and more edges are rewired, the Wasserstragas networks become more and more asymmetric until it becomes indistinguishable from an ER network with the same number of edges, and its S saturates to that of an ER network. On the right, we're showing 6 examples of Wasserstragas networks with fixed number of edges, but at different rewiring probabilities. We can see that at low rewiring probabilities, the node permutation matrix is very orderly, either shows a rotation of all nodes as a whole or an approximate reflection plus a rotation of all nodes. When the rewiring probability is high, we observe an interesting phenomenon, which is that a part of the nodes are rotated as a whole, part of the nodes are reflected and rotated. And when P is 0.55, the network is basically as asymmetric as an ER graph, which can be observed in the node colors in the permuted network, and as well as the node permutation matrix, which is pretty much random. The fourth model we looked at is the stochastic block model. So here we observed a very interesting effect, which is that the communities in an SBM network are very similar to each other. Therefore, in the optimal node permutation matrix, we can see that the nodes from different communities are actually switched. So in the first example, when there are 2 communities, the nodes are switched. When there are 3 communities, 2 of the communities are switched, whereas in the third community, the nodes are mainly only scrambled. At last, we applied our measure to some real-world networks. The first one is the C. elegans brain network, which nodes are colored based on which hemisphere they belong to. And we can see that after the node permutation, most of the nodes are permuted to the opposite hemisphere. And on top of that, a lot of nodes are actually permuted to their counterparts in the other hemisphere, represented by the non-zero elements on the diagonals of the diagonal 2 blocks in the P matrix. And the second example is the macaque brain network, in which each node represents a brain region in the network. And we can see that this network, in fact, has really, really high bilateral symmetry, whose node permutation actually flipped the 2 hemispheres of the brain exactly. And note that even though the 2 hemispheres are flipped exactly, its E is 11.99 instead of 0, which means that the 2 hemispheres of the brain are actually different, slightly different from each other, which means that the network does not have a perfect symmetry, but has a high level of approximate symmetry. And this is a good example of why having a definition of approximate symmetry and the measure for approximate symmetry is important. Thank you.
Well, thank you very much. We are quite late, so we have a time for a very quick question. I think that I've seen one on the chat.
I can't see the question. I'm sorry.
How are the permutations chosen to compute the symmetry?
I'm sorry, I didn't get that. I'm sorry, could you read the question again?
How are the permutations chosen to compute the symmetry?
So, for example, if a network is symmetric, then there definitely exists a permutation. For example, in this 2D lattice here, we can permute the left and right half of the network, and the network remains exactly the same. So this suggests that we can use a node permutation to define or measure the level of symmetry of a network.
Okay, thank you very much. Is anybody wants to ask a very quick question?